Okay, the next presentation is a reduction of CM noise by minimizing near field effect in a DC-DC converter. And the presenter is Tyler McGrew. Tyler got his bachelor degree from the Miami University in 2021. Right now, he is a PhD student in the CPES, and his research is about the high frequency power converter and the EMI study. Okay, please, Tyler.
Okay, good afternoon, everyone. My name is Tyler McGrew, and the topic of this presentation is reduction of common mode noise by minimizing near field effects in a DC-DC converter. So I'll start by giving some background on near field couplings and power converters, and then I'll introduce a buck converter where the conducted common mode noise is strongly impacted by the location of the EMI filter relative to the power stage due to some near field coupling effect. And then I will show how we identify the mechanism of this near field coupling. Next, I will show how we derive a common mode noise model for this converter, which includes the effect of parasitic capacitive couplings. And finally, we'll explore different shielding techniques to reduce the coupling and reduce the common mode noise, and wrap up with a conclusion. So near field couplings refer to parasitic capacitive and inductive couplings between different areas within a power converter. The displacement current through a capacitive coupling is equal to the mutual capacitance and the dV/dt, while the voltage induced by an inductive coupling is equal to the mutual inductance times the dI/dt. As we know, wide bandgap power devices are finding increasing adoption in many converter applications, and converters using these devices can take advantage of higher switching frequencies and faster switching speeds. However, these factors also increase the dI/dt and dV/dt within the power stage. Converters using these high switching frequency can also use smaller passive components for more compact converter layouts. However, this also increases the mutual couplings between these different areas in the converter. As a result, the challenges presented by parasitic couplings will continue to increase with the further adoption of wide bandgap power devices. So in this work, we investigate the conducted common mode noise of a single phase buck converter with a single stage EMI filter. And this converter uses 600 volt gallium nitride devices, as well as a separate PCB inductor daughter board. Also, this converter has gaps in the converter PCB, which will allow for the evaluation of different shielding techniques. So here's the setup for the conducted noise measurement of this converter. The conducted noise is measured using the line impedance stabilization networks, which we'll call LISNs. And here there's 50 centimeter input power cables between the LISNs and our converter. For this work, the converter is operated at a 125 to 62 volt step down and a switching frequency of about 600 kilohertz. So the first test is to measure the reduction in the common mode noise by adding the EMI filter in its typical position here next to the power stage compared to the baseline noise with no filter. And here we find that adding the EMI filter only reduces the noise by about 10 to 15 dB, which is much less than we would expect for this filter design. Then we do a very similar test, only this time we place our EMI filter very far away from the power stage. Here the EMI filter is 50 centimeters away from the buck converter. And in this position, the EMI filter does a much better job of reducing the common mode noise. So clearly there's some type of coupling between the power stage and the filter. At these distances in the conducted frequency range, we know that this coupling must be a near field coupling effect. And in the near field region, a coupling can be caused by an electric or magnetic coupling mechanism. To identify which mechanism is causing this effect, we can perform a test by placing shielding materials in between the power stage and the filter and measure the corresponding reduction in the noise. So first we'll place a high permeability ferrite shield in between the power stage and filter, which should bypass magnetic fields away from the filter. And with this material, we see a small reduction in the noise. Next, we place a grounded copper shield in between the power stage and filter. And here we see a much better reduction in the conducted common mode noise. So this indicates that this is due to some electric or capacitive coupling mechanism. We can further investigate this electric coupling using electric field measurements, which we collect with this automated near field measurement system, which we have in our lab. So the robotic arm can position the electric field probe over the converter at different points while the converter is running. And then the oscilloscope collects the signal from the probe at each point. So previous work identified the surface mount inductor as the main source of electric field emissions in a buck boost converter. For our work, we identified the PCB inductor as the main source of electric field emissions in a buck converter. So the topology is different and the inductor structure is different, but our finding is the same, which is that the power stage inductor is the main source of electric field emissions. This is because the windings of the inductor have a relatively large surface area, which is connected to the switching voltage of your converter. We can also use the electric field measurements to actually visually identify the coupling from the power stage to the filter. So here is the measured electric field in a planar region just above the EMI filter's typical position, but without the filter present. And here we see that the electric field radiates fairly uniformly from the power stage. Then we do the same measurement, only this time the filter is present underneath this measurement region. And when the filter is present, we see a reduction in the electric field strength. This is because the electric flux lines, which previously passed through this region, have now coupled onto the conductive surfaces of the EMI filter. So this is a further indication of this capacitive coupling. Now that we've identified the mechanism of this coupling, we'll derive a common mode noise model, which includes the effect of these capacitive couplings. So we'll start with our ideal circuit model of the conducted noise measurement, again with our Lisens, EMI filter, and converter. First thing we'll do is simplify the structure of the Lisens to just the 250 ohm noise measurement impedances. Then we'll replace the line-to-line capacitors of the EMI filter and power stage with short circuits because these impedances are very small in the conductive frequency range. Next, we'll replace the two switching devices in our buck converter, which is top switch and bottom switch, with two equivalent noise sources, IS and BS. And these two sources represent the exact current and voltage waveforms in these two branches. When we apply superposition to these two sources, we find that the current source is shorted back to itself. So in this way, the current source cannot produce any common mode voltage at our Lisens, which we'll call VCM. So for this reason, we can remove the current source from the model. Then we can identify 4 areas of low common mode impedance. Here I have them highlighted, and I'll discuss these more on the next slide. But these are called area A, area B, area C, and ground. And we can add the self-parasitics of our EMI filter, including the equivalent parallel cap of our choke, the equivalent series inductance of our white capacitors, and the grounding inductance of the EMI filter. Finally, the most important step of this work is that we add a parasitic coupling between each of our 4 common mode areas to account for any capacitive couplings in the system. So the 4 areas we've highlighted here correspond to different components, traces, and cables in our actual converter. So area A is the input power cables from the Lisens, as well as the input side of the filter up to the choke. Area B is the other side of the filter, as well as the input and output power lines of the converter, including the load. Area C is our switch node and power stage inductor, while area G is the ground. So we actually measured these couplings experimentally, and the values range from about 0.1 picofarad to about 100 picofarad. And the trend is similar to a parallel plate capacitor, which is that the mutual coupling is stronger when the 2 areas are larger and close together. So we can use these measured values to actually simplify our common mode model. We can remove 3 couplings which have very minimal impact on the measured common mode noise. The coupling from area A to ground is in parallel with the low impedance of our noise measurement. And because this is in the range of picofarads, it has no impact on the conductive noise. Similarly, the coupling from area B to ground is in parallel with the much larger capacitance of your Y capacitors, so we'll have very minimal impact on the noise. Coupling from area B to area C is here in parallel with our noise voltage source. So because it's a capacitance in parallel with the voltage source, it will have no impact on the conductive noise at the Lisens. Then we'll combine the line and neutral. Then we'll lump the impedance of the common mode choke with its parallel caps. We'll call this ZLY, lump the impedance of the Y capacitors with its series inductors, called as ZCY. Finally, we can rearrange our model and we get this simplified common mode model. It consists of a voltage source, which represents the switching voltage of the power stage, two near-field couplings, one from area C to ground, one from area C to A, the measurement impedance for your noise, and these two impedance branches which come from your EMI filter. We can verify the accuracy of this model by predicting the common mode noise spectrum. First, we'll predict the noise with the filter and its typical position next to the power stage. The noise source for the converter and for our noise model is the switching voltage of the power stage. And here's the measured switching voltage in the frequency domain. So we applied the FFT to the actual switching voltage of our converter. To predict the noise at our listens, our measured common mode noise, we can derive a noise gain from our source to our measured noise as a function of these impedances in our model. And because we already know the values of these different impedances, we can calculate this noise gain, which we'll call GCM, which is the ratio of our measured noise to our noise source. And here's the calculated or predicted noise gain overlaid with our measured noise source. And if you multiply your noise source with your noise gain, we can predict the actual measured noise spectrum. And here we find close agreement between our predicted noise spectrum and our measured noise spectrum, which verifies the accuracy of this model. We can also verify the accuracy of this model with the filter moved away, just as another example. In this case, because this filter is very far from your power stage, this near-field coupling CAC, which is from the input side of your EMI filter to your power stage, is minimized because this distance is so great. So in this case, your noise source is the same because it's just the switching voltage of your converter, which is unchanged. However, your noise gain is changed by removing this coupling from your circuit. And here we find also pretty good agreement with our measured noise. Now that we've verified the accuracy of this model, we will try to analyze it to get a better understanding of how to effectively reduce the common mode noise. So it may seem obvious to just try to minimize the noise source. However, because this is the switching voltage of your converter, you can't reduce this very much without affecting your converter's operation or efficiency. So the more effective way to reduce noise is to minimize this noise gain that we discussed. And this is a function of all these impedances, and it may not be very clear how to effectively reduce this noise gain. However, we can notice that all the noise must go through one or both of these capacitive couplings. So what we're going to do is a bit of an approximation. We're going to individually analyze the noise which is generated by current through one of these couplings while we set the other coupling to 0, and then we'll do vice versa. So first, we'll analyze the noise which is generated by the current through coupling from area C to ground. So this is kind of our traditional noise path, where the EMI filter effectively attenuates the common mode noise because the Y capacitor branch bypasses current away from the listens, while the common mode choke branch attenuates current, which will go through the listens. So for this reason, the noise gain through this path is pretty small. Then we'll look at the noise which is generated by the current from area C to area A, and we'll set this other coupling to 0. In this path, the EMI filter actually does not attenuate the common mode noise because once the current flows through this coupling, it faces only a low impedance from your listens and your Y capacitor branch. And here you see that this coupling path is actually much stronger than this converter with our measured values. Compared to our total noise gain, we see that this near-field coupling path is the dominant common mode noise path in this converter. So to minimize the noise, clearly we should try to minimize this coupling. So this coupling, just to reiterate, is between this power stage inductor and the input side of our EMI filter and the input power cables. To minimize this coupling, we can either shield our victim area A or our emissions area C. And we'll try both of these techniques. First, we'll shield area A. To do this, we cover the input power cables and EMI filter with copper tape, which is tied to the ground plane. The model is slightly modified. There's now some coupling between area A and the shield. However, this coupling is just in parallel with a very small impedance of our listens, so it has basically no impact on the noise. You still have some coupling from area A to C. Even though you shielded area A, there will always be some leakage flux. But in this case, the coupling is effectively reduced by over 30 times. As a result, using our model, we predict a noise reduction up to 30 dBs the shielding technique. And we test this experimentally. Here's the baseline noise, and here's the noise with our area A shielded. And our predicted noise gain is pretty close, actually. Sorry, predicted noise reduction is pretty close to our measured noise reduction. So shielding the input power cables in the EMI filter is an effective way to reduce common mode noise if you have some near field coupling effect. In many practical applications, the converter is already enclosed by a metal case, which is grounded. So you don't have to worry about coupling to your input power cables. So here we just emulated this condition by only shielding the input power cables, but not, not shielding the EMI filter. However, we find even without coupling to the cables, this near field effect is still very strong. So practically, you probably also want to shield the EMI filter. We can also shield the emission source instead of shielding our victim area. So because the inductor is the main source of our electric field emissions, here we cover the entire inductor in a copper box, which is tied to ground. Again, the model is different. Now I have a coupling from area C to the shield. In this case, our near field coupling CAC is still effectively minimized because we shielded the emission source. However, we actually increased the coupling from our switching node to ground. So for that reason, although our high frequency noise should still be reduced, actually we won't see any benefit at the low frequency because the coupling from area C to ground is worse at the low frequency due to the design of the EMI filter. So here's our measurement result compared to our predicted noise reduction. And as we predicted, there's actually no reduction in the common mode noise at the switching frequency, although we still get some benefit at high frequency. So practically, this is not a very useful technique in many situations because you don't get reduction at your low frequency, which is often the strongest harmonic. So the better way to shield your emission source is to shield the inductor to neutral. And by neutral, I mean the return or common negative of your power stage. So in this way, your coupling from area C to the shield is now just part of your coupling from area C to area B, because your neutral is part of area B. And because this is in parallel with your voltage source, again, this coupling has no impact on the measured noise. So this is a better way to do this shielding technique. And this coupling between area A and C is minimized again, and you get an added benefit of reducing the noise, which is coupling from area C to ground, because you shielded your main emission source to some point other than ground. As a result, we predict effective noise reduction. And our experimental results, again, are pretty close to our measured noise. And shielding your emission source to neutral or some other DC potential on your converter is an effective way to reduce your common mode noise. So in this work, we identified a near field coupling effect from buck converter with the EMI filter, which increases the common mode noise. Then we identified the mechanism of this coupling as electric fields coupling from our power stage inductor to our EMI filter. We developed a common mode noise model, which includes the effect of near field capacitive couplings, and we use this model to accurately predict the measured noise spectrum with the filter in 2 different locations. Finally, we demonstrated how shielding the inductor or the EMI filter can effectively reduce the CM noise. So that's all for my presentation. Thanks for your attention.